Hello, today we're going to be looking at building an electrochemical cell. Now, electrochemical cell is basically a nice word for battery. A battery produces voltage, so another word that we use for a electrochemical cell. So I'm going to write these down. We're going to be looking at electrochemical cell. We also call them voltaic cells. They are exothermic, which means they produce energy. And we also call them batteries. All right. So by learning what this is all about, these are all this cluster of words right here means all the same thing. Electrochemical means you're having two chemicals that are producing energy. Voltaic means that you're producing voltage. Exothermic means we're producing energy. And batteries are our street name for two metals in a solution. Anyhow, so I'm going to kind of ask questions as I go through this. We're going to build a cell together, and hopefully you'll be able to answer these questions as I kind of go through this with you. Okay, so the first thing is I'm going to need two beakers. Okay, so these are beakers that I'm drawing right here. We are going to need a metal in here, and we're going to need another metal in here. So we're going to put a little switch. Well, there's usually a voltmeter on there, and there is something missing. So the question is, do you know what would be missing in this picture? Hopefully your answer was, I'm going to be missing that little U-tube right here. Not U-tube as in the computer. We're talking about a glass U-tube that pretty much is packed with salt. So this thing right here, surprisingly, is called the salt bridge. You can actually use NaCl in this, and I have used it before. It basically has salt packed in here and glass wool in the bottom so that the salt doesn't fall out. And then we have solutions inside of here. So we'll make these kind of nice and blue so that they look like solutions. All right, now the next thing that we're going to do is we're going to kind of pick a metal off our reference table. So I'm just going to pick two metals. We're going to pick this metal, aluminum, and I'm going to pick this metal, zinc. Like if you had aluminum and zinc, you can label them on either side. It doesn't matter what side you want to, but I'm going to put my aluminum over here just to make this interesting, and my zinc over there. All right, so when we go ahead and look at this, we have to know how to read reference table J. And it turns out the one that is the more active metal is this guy right here, aluminum. Now, the nice thing about this chapter is it's organized in such a way that a lot of these things are alphabetical. And you might be saying, what do you mean alphabetical? Well, in this is going to be my oxidation. This is going to be my reduction. Notice that O comes before R in the alphabet. So when I'm going to look at what is my oxidation, I'm going to put all my information over there about oxidation and my reduction right over here. Well, as you know, oxidation always will start with an element, and a reduction will start with an ion. Now notice that E comes before I in the alphabet. And as you recall from writing these reactions, an oxidation will always start with one item, and it will become two. So with an oxidation, what's going to happen is the metal will fall apart. So we start with aluminum, the element. It becomes aluminum, the ion. That's the only thing metals can do is lose. So oxidation is losing. Reduction is gaining. Oil rig. Now, to go from 0 to 3, that's going to take 3 electrons. My reduction is going to be simply start with the this right here as an ion. The only option I have is zinc plus 2. I'm going to need to gain a certain amount of electrons to become zinc the metal, and that would be 2 electrons. Notice mathematically if this is making sense. 0 equals 3 plus a negative 3. 3 minus 3 is 0. And on this one, 2 plus a negative 2 equals 0. That makes sense. So if you notice the pattern, my oxidation always starts with 1. My reduction will start with 2 items. So 1 comes before 2, O comes before R, and the element comes before the ion. So this kind of all falls into play here. Now, if we take a look at what's going on, if this reaction on the left is losing electrons and the reduction is gaining the electrons, that means the electrons are flowing through the wire from the aluminum to the zinc. So when this switch gets closed, the electrons are going to flow that way. All right? So that's how the electrons flow. And what's going to happen over time is we're going to notice that the aluminum is going to kind of crumble apart. So if we look at this over time, this is what the thing will look like after a while. All right? The aluminum will kind of get eaten away. Now, where does the aluminum go? The aluminum goes into solution as an ion. So that's why the aluminum is crumbling apart. If you notice this reaction here, it's saying the metal is turning into the ion. So what's happening with the metal mass is over time, the mass here decreases, the ion concentration. Since the mass is crumbling apart, the ion concentration goes up. In this case, the ion concentration over time, the ion conc will be going down, and the metal mass will be going up. So just read the story from left to right. That's it. As long as you wrote the half cell correct, it'll make perfect sense. All right. Now, the only things left are just to discuss what is this item right here, and what is this item right here. These are agents. Now, think about what's going on here. An oxidation means it is losing electrons. So what's happening with this aluminum losing electrons is actually causing the other reaction to do something. Well, what's the other reaction doing? The reaction that aluminum is kind of triggering, this aluminum right here, although it's undergoing oxidation, it's known as the reducing agent because it's causing the number right here of zinc to go down, okay? And that zinc plus 2 is allowing the electrons to have a place to go, so that is my oxidizing agent. The agents are always opposite of the process they undergo. And that right there basically covers what's going on. As the zinc metal is coming out of solution, we're going to have whatever its compadre is, the negative ion, is going to build up here. And say you had like zinc nitrate. The NO3 ions are going to build up and you have a lot of negatives. So what they're going to do is they're going to kind of migrate up the bridge, and the excess aluminum ions, they're going to migrate up the bridge. So the bridge is really allowing ion migration in both ways. Now this will continue to produce electricity, volts, as long as there are the two metals there. But as you know, the aluminum is crumbling apart, so at some point it's all going to dissolve into solution, and at that point we say that the battery is dead when you have 0 volts. So if you turn on a flashlight and it's dim and barely staying alive, at that point we say that the reaction has reached equilibrium. That is a point at which the reaction is losing its pizzazz, and that's the story. So just wanted to let you know how that worked, and that's it.